Right, so 5.3 deals with complex vector spaces. So just a quick review of complex numbers. A complex number is a number that comprises of two parts. The one part is called the real part and the other part is the imaginary part. Now complex numbers have this form where A is a real number and B is a real number, and I denotes the square root of -1, imaginary number. Right, so again we call the real part of ZA and we call the imaginary part of ZB, and also the modulus of Z is simply the square root of the sum of the squares of the real and imaginary parts. And then also we call the conjugate of Z, denoted by Z bar, as the complex number Z that you take, but you change the sign. You change the sign from plus B to minus B. Okay, and that's called a complex conjugate. And then also the complex number Z multiplied by its own conjugate is pretty much, you can go and work that out, that's always a squared plus b squared, and that is the modulus squared. Right. Right, now the argument of Z is called theta. Okay, and again remember we can always go and represent the complex number Z on the complex plane, right? So there's the complex number Z. And remember, we can basically go and represent it as a coordinate point. Okay, and basically the argument of Z is pretty much going to be that angle there. Okay, and we can go and write Z in polar form. And remember that is the modulus of Z. Okay, so basically you can write A over the modulus of Z as the cosine of the angle theta. Right, so you can go and solve for A as Z, the cosine of theta. And so that's the term that you get there, and you can also do the same for the B part. The B you can go and solve as. The B part you can solve as then the modulus multiplied by sine theta. So that's just the polar form of a complex number. Okay, and again the set of all complex numbers will be denoted by C. Okay, and remember, a vector space in which the scalars are allowed to be complex numbers is called a complex vector space. So this is just another definition. If n is a positive integer, then a complex n-tuple is a sequence of n complex numbers, just like in the case of the real numbers, real numbered vectors, real number component wise I'm talking about. The set of all n tuples is called the complex n space, and it's denoted by Cn. Now Cn is equipped with component wise operations. So component wise addition and scalar multiplication. It works in the same way as normal real number multiplication and addition. And under those two operations, a complex it's a complex vector space. You can go and check that all the properties of a vector space, all the properties that need to hold, are satisfied. All those axioms we did in the first semester. Next we've got the example there. If you have two vectors in C2 and K is a complex scalar, they just ask us to find that. Now it works normally, so the sum between U and V is, take that term there, take that term there, take that term there. Okay, so that is how addition works, and then scalar multiplication. Okay, U is that vector there, Take that vector there, that vector there, take that vector there, take that vector there. Okay, that's your second component, and that is equal to, that's equal to that. Okay, and there we've got our vector. So that's how multiplication, scalar multiplication works. Alright, so note that every vector can be split into two parts. It can be split into a vector corresponding to the real part and a vector corresponding to the imaginary part. Okay, and again, the complex conjugate of a vector v will be just the imaginary part that you take and you change that sign from a positive to a negative, right? So the complex conjugate of v is going to be this. Then matrices with complex entries are called complex matrices. And if A is a complex matrix, then the real part and the imaginary part are matrices formed from the real and imaginary parts of the entries of A. And the conjugate of that is the matrix formed by taking the complex conjugate of each entry in A. So if you look at the real part, real part of that matrix, it's going to be formed by those entries there. Look at the imaginary part, it's going to be formed by those entries there. Okay. And what is the conjugate of A? Conjugate of A is going to be the conjugate of each one of the entries, okay, which is going to be that and that. So the determinant of A is like it is normally. It's this entry multiplied by that entry minus that entry multiplied by that entry there. Okay, so that you can just simplify as, right, and that is equal to, okay. Right, next is just some algebraic properties, which I'm going to leave for you guys to verify on your own. Theorem 1, if u and v are vectors in Cn, and if k is a scalar, complex scalar, the conjugate of the conjugate is u. That's pretty obvious. If you change the sign and you change it again, it's going to be the original vector. The conjugate distributes over the scalar multiples as well. That you guys can go, so the conjugate of a scalar multiple of u is the same as the conjugate, is the same as the conjugate of u, and I take a scalar multiple, and the scalar in this case is the conjugate of k. Alright, so and that can also be easily verified. If you take the conjugate of the sum of two vectors, it's the sum of the conjugates. If you take the conjugate of the difference between two vectors, it's the same as the difference between the conjugates. Then when it comes to matrices, if A is a m by k complex matrix and B is a k by n complex matrix, it works the same there. If you take the conjugate of a conjugate, that's the matrix A, the conjugate distributes over the transpose. That's pretty obvious. And the conjugate, although it's a little bit more tricky, you guys need to go and verify that. If you take the conjugate between a product of two matrices, it's the same as the product of the conjugates. Then just a note on the complex Euclidean inner product. If you have two complex vectors, v, u and v, and you look at the dot product, the dot product is a little bit, it's differently defined. The dot product between u and v is pretty much going to be defined as, again, like the normal dot product, you multiply each vector component-wise, right? But the difference here is you are taking the conjugates of each one of the components there, and you're multiplying it through like that. So we can also define the Euclidean norm in Cn. Next we have the example. They ask us to find the dot product of u and v. By definition, it is basically we take that term and we multiply it with the conjugate of that. We add that to that term multiplied by the conjugate of that, and we add it to that term multiplied by the conjugate of that. Writing that down, we get that expression, and that is then equal to, and adding all of that together we get this. Okay, and what is the norm of V? Norm of V is the square root of the dot product with V with itself, and by definition we know that is. So that is going to be the modulus of the first component squared plus the modulus of the second component squared plus the modulus of the third component squared. Right, and that we can go and look at that individually. Right, so the modulus of 3i is going to be the square root of 0 squared plus 3 squared, which is 3. Okay. The modulus of 1 plus I is going to be the square root of 1 squared plus 1 squared, which is the square root of 2. And the modulus of 2 is going to be 2 squared plus 0 squared, square root of that, which is 2. So that's going to be the square root of 15. Right, the following theorem just gives us some properties of conjugation and the dot product. Okay, so I'm going to leave all of this for you guys to verify. If U, V, and W are vectors in Cn, and if K is a complex scalar, then the complex Euclidean inner product has the following properties. U dot V is the same as the conjugate of V dot U. And also the in terms of this complex Euclidean inner product, the distributive property holds. So if you've got a sum between two vectors and you take that Euclidean inner product with vector U, it's the same as taking the Euclidean inner product with each vector and the sum individually and then adding it together. And scalar multiplication also works similar to the normal dot product. That is, if you take Euclidean inner product of a scalar multiple of a vector with another vector, then it's just the same as taking the dot product with the two vectors and then multiplying that with a scalar. Right, it works a little bit different now if you take a scalar multiple, if the second vector in your dot product is a scalar multiple, then it's a little bit different. So there, definitely the order is important. If you take the dot product of a vector with the scalar multiple of another vector, it's the same as taking the dot product with the two vectors on their own, and then on the left multiplying that with a conjugate of k. And also again, if you have this complex inner product at least 0, and you have that that dot product is 0, that happens if and only if V is the 0 vector. So one can also go and verify that quite easily. Right, so just some the next theorem, theorem 4. If lambda is an eigenvalue of a real n by n matrix A, and if x is the corresponding eigenvector, then the conjugate of this eigenvector, because it could be a imaginary number, and so it could have an imaginary component. The conjugate of lambda is also going to be a eigenvalue of A, and the conjugate of x is going to be also the corresponding eigenvector. Right, so if lambda is an eigenvalue and x is the corresponding eigenvector, then we can go and take conjugates on both sides. So we can take the conjugate of that, and we can take the conjugate of that, and that is pretty much going to be the conjugate always distributes over product of matrices. And because A is a real valued matrix, its conjugate is going to be itself. And that implies, therefore, that the conjugate of lambda is also going to be an eigenvector. The conjugate of lambda is going to be an eigenvalue of A, and the conjugate of x is going to be its corresponding, is going to be a corresponding eigenvector. Right, so again, the question, this question is just ask us, find the eigenvalues and the basis for the corresponding eigenspaces of A. So we first determine the eigenvalues of the matrix A. So there's my matrix A, and what I do is I set up this equation, right, and then what I do is I find the determinant of this matrix. Okay, that is equal to, okay, and from there, that is equal to lambda squared plus 4. So the eigenvalues become, that happens if and only if, and that happens if and only if lambda is 2i or lambda is minus 2i. Finding the basis for when the eigenvalue lambda is 2i, that is going to be, alright, and that's going to occur when 2i plus 1 is 1, and there we've got 2i minus 1. So we are interested in this matrix. We are interested in what happens to that matrix. So we're gonna look at all vectors x, y such that that's in the null space, and x, y is a non-zero vector. Now that matrix reduces to, okay, and all we want to do is we want to just go and look at the following. We want to just see what happens to that. Can we go and simplify that? We can simplify it by multiplying in the denominator with the conjugate. So the conjugate in that case is going to be minus 2i plus 1. And what we do, we have to do that there as well. So that's going to become that, and there we've got, we've pretty much got a fifth minus a 2/5 multiplied by the complex number I. Okay, so my matrix now becomes, right, so that is the same as this. Okay, there we go. So our aim now is to make that 0, and we do that by adding 5 times the first row to the second row. Right, so we take our entry there. Okay, our matrix reduces to that, and now we can go and introduce a parameter. Right, so that corresponds to that there. Okay. So my vector becomes, alright, so the basis vector, the basis for that, the basis for the eigenspace corresponding to the particular eigenvalue is, right, so there we've got our basis. So now taking the matrix A, we have calculated the eigenvalues as minus 2i, 2i respectively. And now what we need to do is we need to find the eigenvectors that correspond to the number minus 2i. Now that's not a difficult thing to do. We do that by finding this matrix for the value minus 2i, okay. Right, so that becomes that matrix, and again we look at the null space of that matrix. So let's take it and go and reduce it. Right, so we make this term a leading one, and therefore we are going to have to just look at what this term is equal to. Okay, so we just look at that separately, and again, how do we simplify that? We take that term and we multiply with 1. So we're going to multiply with the conjugate. So we're going to multiply with 2i plus 1. Okay. And what we do for the denominator, we must do for the numerator as well. So we're going to take that term and we're going to multiply it there as well. Okay. Right, so that becomes, right, simplification yields that. So there we've got basically that becomes the complex number a fifth plus 2/5 I. So that matrix then becomes, we have, okay, that's that. And now you can further simplify that and again reduce it even further. Okay, there we've got it. And that then becomes, and you can go and do that. Okay. So now, now it's easy to find the basis. Again, introduce the parameter t for the variable y. We can then go and solve for the variable x in terms of the parameter t. Right, so there's our solution, and so the basis vector for the eigenspace corresponding to that matrix is right, so we have to multiply that with a minus. Okay, and we've got our vector. Right, so the basis for the eigenspace corresponding to lambda equals a half is going to be this vector, that vector there. Okay. Right, so theorem 5, I refer you guys to the textbook for the proof. Theorem 5, if A is a 2 by 2 matrix with real entries, then the characteristic polynomial of A is this. And again, the characteristic polynomial, we determine this from the determinant of lambda I, where I is a 2 by 2 identity matrix. We look at the determinant of that. That is a 2 by 2 matrix, and it's easy to find the characteristic equation. So now it's just this is a polynomial of degree 2, and we know when that polynomial has real roots and when it doesn't. Okay, and so we calculate the delta, which is b squared minus 4ac, right? And b squared is that term there. A is that term there, which is 1. And the C is the determinant of A. Okay, so applying that, we see that to have distinct real eigenvalues, you need a bigger than 0 term. To have to have one eigenvalue, we need that delta to be 0, and to have complex eigenvalues, it needs to have a delta strictly less than 0. Okay, so that's not difficult to see. Theorem 6, if A is a real symmetric matrix, then this symmetric matrix has an interesting property. It's always going to have real eigenvalues. So if we let A be a 2 by 2 real symmetric matrix, let's assume that it has a complex. Let's say it has a complex eigenvalue. Right, so suppose that A is a complex eigenvalue, and let X be a vector, eigenvector corresponding to lambda. Then obviously we've got that A and X and lambda satisfies that equation. We know that implies also that the conjugate of X is going to be the eigenvector corresponding to the conjugate of lambda multiplied by the conjugate of X. And then we can multiply with the transpose of X on both sides, and essentially what you're going to have is you're going to have a dot product, and that is the dot product between the vector X with its conjugate. And we know that that is equal to lambda times the norm of X squared, which is a real number. So that is going to imply that we can go and solve for lambda as a real number. Well, possibly not. We don't know yet if it's a real number. We'll establish that just now. Okay, and we just need to show that this thing here, that is a real number. Right, we can show this is a real number by showing that the conjugate of that is equal to itself. Because remember, conjugation of is going to only influence a complex number that has a non-zero imaginary part. So if we can show that, we are done, right? So that is what we need to show. So from there we have, okay, and the conjugate of the conjugate is X, and the conjugate of a product, and it transfers over a product. Okay, and it's also going to transfer over a transpose. And that is equal to that. That is real, so it's not going to affect it. Right, we can show this is a real number by showing that the conjugate of that is equal to itself. Because remember, conjugation of is going to only influence a complex number that has a non-zero imaginary part. So if we can show that, we are done, right? So that is what we need to show. So from there we have, okay, and the conjugate of the conjugate is x, and the conjugate of a product, and it transfers over a product. Okay, and it's also going to transfer over a transpose. And that is equal to that. That is real, so it's not going to affect it. Right, so just if you look at the last right, so theorem 7 states something about 2 by 2 matrices that have real valued entries. So if A is a real 2 by 2 matrix with complex eigenvalues, right, and you get a situation where you have two conjugate complex eigenvalues, where specifically B is not 0, then if X is an eigenvector of A corresponding to lambda equals A minus BI, then this matrix that you form, which is matrix P. So how you form this matrix P is you divide, remember the vector X. The vector X is going to have the following form. Right, it's going to have that form. So the X part is going to be possibly a complex number, and the Y part is going to be possibly a complex number. So this matrix P that you form is, all you do is you form this matrix by dividing the real and the imaginary parts up. So you let your first column and your first row entry be C. Then you let your second row first column entry be E, and then you look at your complex component. So that is the matrix P. That's how you define the matrix P. Right, so then if you define P in that way, then P is invertible, and you can actually express A as P times this matrix here times the inverse of P. Now, note that you form this matrix from the eigenvalue lambda. That's where you get the A and the B from. Okay, so we're going to look at why exactly is this matrix P invertible, and why can you express A in that particular form. Right, so recall, okay, so let X be the eigenvalue for lambda, the eigenvalue corresponding to lambda. So remember now, if you take this equation here, then AX is lambda, where lambda is now that complex number multiplied by that vector there. Right, so that translates into this equation. Okay. So that's my X, that's my lambda, and that is that's AX. Okay, so now I just want to observe the following. Let's just go and look at that term on its own. Okay, and go and multiply that out quickly. Right, so we get that, and then multiplying it out quickly, you get that there. So again, we're taking A1 and we're multiplying it with that whole vector there. You get that, and then you take that vector, or that entry there, and you multiply it there with that, and you get that there. Okay, and then you do the same for the second row. Multiply that with that, and you get this term here, and then you multiply that with that, and you get this term. Okay. Right, so then grouping the real part, separating the real and the imaginary parts, we get this matrix, okay? And now we can just view that in a little bit different way. We can separate that into a matrix containing a real and an imaginary part. Okay, so you can write that as a product between two partition matrices. Now I'm talking about the partition in terms of separating the columns indicate the first column indicates the real part and the second column indicates the imaginary part. Right, so the A11 you can write there, and then you write the A12 there, and then you can take the C there, write the E there, and you can write the F there, okay? Right, so that is the actual matrix P. And this matrix is partitioned into two columns. The first column indicates the real part and the second column indicates the imaginary part. Right, now looking at the other side, the vector x multiplied by lambda, that you can go and multiply out in the normal fashion. Right, so you multiply this complex number with that entry and you multiply the complex number with that entry. Right, so then you go and gather your imaginary terms together and you separate the real from the imaginary, and then again you can go and write this vector as a product between two partitioned matrices. Okay, so again you've got you can write that as two 2 by 2 matrices, again in the same way. So you take your C there, you take your D there, take your E there, you take your F there. Okay, then you take your A, put it there, take your B there, then you take your, you put your A there, because that corresponds to the D, and your minus B you put there. Right, so this is that other matrix we talked about that you get from lambda A minus BI, okay, and this is your matrix P. Right, so now we've got we've identified our matrix P, and now we just need to make sure that this P matrix that I've constructed, why is it invertible? Is it invertible? That's the question. Right, so to find out whether that matrix P is in fact invertible, remember we want to find that remember P is this matrix here that you formed from an eigenvector. And the eigenvector is the eigenvector that corresponds to this eigenvalue, right? So now what you want to do is you want to actually just see what do the eigenvectors of what do the eigenvectors corresponding to lambda look like? And how did we determine this? We set up this matrix, and then we look at where that matrix is not invertible. It's not invertible, or in other words, where the determinant is 0. That's equivalent to just looking at all vectors, non-zero vectors x, where where X is in the null space of this matrix. Right, so now remember that essentially lambda makes the determinant of that. Lambda must, because lambda is an eigenvalue, lambda must make the determinant of that matrix equal to 0. Right, so let's look at two cases. What happens if A1, if this entry is 0? Well, then I can make this a leading one because that term is not 0, because we said initially that B is not 0. So that is imaginary number is definitely not going to be the 0 number. So I can make it a leading one, and that term is just going to become 0. So now I can go and further reduce this matrix here. I can get rid of that entry, and this entry I can't get rid of. Well, that entry essentially it has to be 0 if lambda is an eigenvalue. It has to be 0. If it's not 0, then the determinant of this matrix cannot be 0, and that's going to contradict the fact that lambda is an eigenvalue. Okay, so basically that matrix is going to reduce. It's going to reduce to something that looks like this. Right, so then from there, that has to imply that basically this term has to be 0. Because otherwise lambda is not going to be an eigenvalue, right? So that is going to imply that A22 is going to be the complex number, and that is not 0. Okay, but that's a contradiction. Why? Because remember the entries of A are real numbers. It's a matrix with real entries. Okay, so that can't happen. So therefore, A12 cannot be 0. Right, so A12 cannot be 0. Right, so we can take our matrix and we can make this term here a leading one. And now we just need to go and look at what that term looks like, which we will do now. Can this thing be 0? The answer is no. But let's just go and simplify that quickly and see what it looks like. Right, so let's check our term out there. What we're going to do is we're going to multiply the denominator with the conjugate, and then we're going to, what we do to the denominator we must do to the numerator as well. So we're going to take that and multiply it with that. Okay. Now on if we go and simplify that, it becomes right. So there we've got our expression in the numerator and denominator, and then further simplifying that, we obtain the final term. So basically, note that this term is non-zero. This we don't really worry about, okay, because this is positive. So it's at least 0. This term is not going to be 0 because A12 is not 0 and B is not 0. And again, that we don't really worry about. So going back to our original matrix, as I said, we can make this a leading one. And now this thing we simplified as, that is the term we got. And again, this is a non-zero term. It's non-zero. Right, so now we can go and eliminate this term here. We can make it a 0, and we can also make that a 0. All right, so we can further reduce this matrix, and now we can go and find the basis for the eigenspace corresponding to lambda. So my basis is going to become, okay, so basically we introduce a parameter t for the variable y, and so that is going to be t, and then we solve for x in terms of the parameter t, and we are basically going to get that term there. Okay, again. And that is going to be our vector. Okay, so the basis is going to be, again, it's going to be that term, 1. Okay. So now that we've got that, we know what our vector x looks like. So now we can go and check that in fact that matrix P that we talked about is in fact, it's an invertible matrix. Okay, so there's our matrix P. How did I form that? Again, it's a partition matrix, partitioned into a real and an imaginary part. The vector y has got a real part of 1, and it's got an imaginary part of 0 there, okay. And then the vector x has got it's got a real part, which is that part there, okay, which is exactly that part there, and it's got an imaginary part, which is that part there, okay, which is exactly that part there. Okay. So now, okay, so this is what P looks like. So the question is, what is the determinant of P? What is the determinant of P? It's that term multiplied by that term, which is 0. And then from that, you subtract this term multiplied by that term. Right? Now, first of all, like we said, this term is a non-zero term because A12 is not 0, B is not 0, and we don't know what that is. It doesn't matter, it's positive, and that is not 0. So so basically it follows that the determinant of P is not 0, so therefore P is invertible. Okay, so we've basically we've proved that A times P is equal to P times this matrix here, minus B, B, A. And from there then, because P is invertible, you can actually you can go and factorize A as P times that matrix multiplied by P's inverse. Okay, so you can always do this. And P will always be invertible. Okay, so next let's look at this example here. They ask us, show that this matrix A can in fact be factorized into that part there for sum A, B, and P being an invertible 2 by 2 matrix. So now that we understand how this proof works, this is really not a difficult problem to do. So we can easily calculate the eigenvalues of A. well, we have calculated it. So let's quickly look at this problem. Right, so now taking the matrix A, we have calculated the eigenvalues as minus 2i, 2i respectively. And now what we need to do is we need to find the eigenvectors that correspond to the number minus 2i. Now that's not a difficult thing to do. We do that by finding this matrix for the value minus 2i, okay? Right, so that becomes that matrix. And again, we look at the null space of that matrix. So let's take it and go and reduce it. Right, so we make this term a leading one, and therefore we are going to have to just look at what this term is equal to. Okay, so we just look at that separately, and again, how do we simplify that? We take that term and we multiply with 1. So we're going to multiply with the conjugate. So we're going to multiply with 2i plus 1. Okay. And what we do for the denominator, we must do for the numerator as well. So we're going to take that term and we're going to multiply it there as well. Okay. Right, so that becomes, right, simplification yields that. So there we've got basically that becomes the complex number a fifth plus 2/5 I. So that matrix then becomes, we have, okay, that's that. And now you can further simplify that and again reduce it even further. Okay, there we've got it. And that then becomes, and you can go and do that. Okay. So now, now it's easy to find the basis. Again, introduce the parameter t for the variable y. We can then go and solve for the variable x in terms of the parameter t. Right, so there's our solution, and so the basis vector for the eigenspace corresponding to that matrix is right, so we have to multiply that with a minus. Okay, and we've got our vector. Right, so that's our vector x. So therefore, what is our matrix P going to look like? The matrix P is going to be the matrix, the partition matrix, the real and imaginary part. That's that, and there we go. That's going to be minus 2/5, and that's going to be 0. And remember, that is an invertible matrix. Now, by the previous theorem, we have that, okay, that must hold. Right, so what is the matrix in the middle? What is the matrix in the middle? That is the matrix that we use, and we get that from the eigenvalue, right? So we said the eigenvalue in this case is 0 minus 2i, okay? So my A is my real part. Right, and then my B, that part there. Okay, so if we take the right hand side separately and we just go and do a little bit of calculation, if we go and multiply that part out first, Okay, so multiplying those two matrices out, we get that matrix, and then we multiply that with the inverse. Okay, and that is equal to, and that becomes this matrix here. And further simplifying, we get that is equal to, that's equal to the matrix minus 1. And that is the matrix A.